transmission lines and waveguides. Coming to guided waves, so I'm going to explain general field equations, TE waves, TM waves, characteristics of TE and TM waves, transverse electromagnetic wave, velocities of wave propagation, wavelengths, impedances. So these are the boundary conditions which are very useful to analyze wave propagation inside waveguides. So one is electric field intensity tangential to conducting surface is equal to 0, electric flux density normal to conducting surface is equal to surface charge density, magnetic field intensity tangential to conducting wall is equal to surface current K, magnetic flux density normal to conducting surface is equal to 0. These are the four boundary conditions useful to analyze wave propagation inside waveguides. So these are the basics of electromagnetic wave propagation. First two are electric and magnetic wave equations. So here suppose wave is traveling along z direction, means rotation is e4 minus gamma from z. Gamma bar is propagation constant. So these are two conducting walls arranged parallelly. It is called as parallel plane waveguide. So here assume wave is traveling along z direction, along x, along y. Assume plates are infinitely extended. So the points along x, along y, there is no variation of field components. So here from two Maxwell equations, I am going to derive general field equations for parallel plane waveguide. So here finally these are four general field equations for parallel plane waveguide. So these are derived from Maxwell equations. So here Ex, Ey, Hx, Hy in terms of either Ez or Hz. So here so in this diagram, along z there is wave propagation, along x there are boundaries. Along x, at x equal to 0 there is bottom conducting wall, at x equal to a there is top conducting wall. So along x there is variation of field components, along y plates are infinitely extended. That means along y there is no variation of field components. So that's why here only there is dou by dou x. So coming to transverse electric waves. Transverse electric waves means here condition is Ez equal to 0. So there is no electric field component along wave propagation. So Ez equal to 0 means here remaining components Ey, Hx, these are not equal to 0. Hz not equal to 0. So by taking electric wave equation here, finally these are the transverse electric wave equations Ey, Hx, Hz. Here e power minus j beta bar z represents wave propagation along z direction. Here m is integer. So for different values of integer m there are different field configurations, and these field configurations are called as modes. So general mode is TE M0 mode. Suppose m equal to 0, solve the field components of zeros. So TE00 mode is not possible. So least possible mode is TE10. So coming to TM waves, here Hz equal to 0 means the general field equations. Hz equal to 0 means non-zero components are Ex, Hy. So here so these are the non-zero components Ez, Ex, Hy from magnetic wave equation. So these are the final equations for TM waves, transverse magnetic waves. Ex, Hy, Ez. So here m equal to 0 means, so here m equal to 0 means Ex, Hy not equal to 0. So least possible mode is Tm00. So coming to cutoff frequency for parallel plane waveguide. So here gamma bar square plus omega square mu epsilon equal to h square. Here h equal to m phi by a. M is integer, a is distance between two conducting walls. So suppose if omega square mu epsilon greater than m phi by a whole square, then gamma is purely imaginary. So then phase constant equation, square root of omega square mu epsilon minus m phi by a whole square. Here cutoff frequency, say at omega equal to omega c, phase constant 0. So from this cutoff frequency equal to cutoff frequency for parallel plane waveguide equal to m phi to a into square root of mu epsilon. So what is cutoff frequency? So cutoff frequency is defined as frequency below which wave propagation stops. So this cutoff frequency. Suppose if operating frequency less than cutoff frequency, gamma is purely real, there is no wave propagation. If operating frequency greater than cutoff frequency, gamma bar is purely imaginary, there is wave propagation. So here, so to get wave propagation between two conducting walls, operating frequency should be greater than cutoff frequency. So that means we can say waveguide is high pass filter. Waveguide is acting as high pass filter. So cutoff frequency, suppose two conducting walls, medium between two conducting walls, medium is free space, then cutoff frequency equal to mc by 2a. Cutoff wavelength lambda c equal to 2a by m. For TE10 mode, cutoff frequency is c by 2a. Cutoff wavelength is 2a. So coming to dominant mode, what is dominant mode? The mode which is having least cutoff frequency, highest cutoff wavelength is called as dominant mode. So in the TE mode, least possible mode is TE10. In the TM mode, least possible mode is TM00. So out of this, TM00 mode having least cutoff frequency, so dominant mode is TM00 between two conducting walls, called as parallel plane waveguide. So TM00 is dominant mode. So coming to TEM waves, transverse electromagnetic waves. So condition is Ez, Hz, both are zeros. Transverse electromagnetic waves means there is no electric field and magnetic field component along wave propagation. For TM wave, suppose m equal to 0. So I am taking TM wave equations. Suppose m equal to 0, then you are getting Ez equal to 0, already Hz equal to 0. So Ex, Hy not equal to 0. That means TM wave is possible between two conducting walls only for m equal to 0 of TM wave. So other than this condition, TM wave is not possible between two conducting walls. So here TM wave is also called as principal wave. So TM wave is possible between two conducting walls. What are the properties of TM wave? So TM wave means fields are entirely transverse. So the amplitudes of field components along the normal to wave propagation are constant. That means here, so cutoff frequency is 0, indicating that all the frequencies down to 0 can propagate along the guide. So cutoff frequency is 0 for parallel plane waveguide, means for TM wave of parallel plane waveguide. So velocity of TM wave is equal to velocity of light if the medium between two conducting walls is free space. Intrinsic impedance of medium is 125.